We're going to continue with string algorithms. We're going to do a couple string algorithms today. We're going to start with something called pattern matching, which is a very classic algorithm. And pattern matching basically is we would like to find one occurrence of a string within another string. So typically, an application for that would be like searching a file. A file, we can think of a file as a big string. And then we can think of whatever we're searching for as a smaller string. So now we can typically we search for a smaller string inside of a larger string. So file searching is kind of a typical application. So let's think about how that would be done. Well, basically, here's how we're going to start out with. We're going to think of the initial idea is going to be what we call a brute force algorithms. Brute force algorithm means that we are going to try every single possibility until we get it right. For example, a brute force algorithm for guessing somebody's password. Let's say you know somebody's password is no longer than 10 characters. Well, what can the password consist of? It's going to be based with characters, could be digits, could be special characters, right? So I don't know exactly how many we have, but if we use capital letters, there's 26 letters, 26 capital letters, that's 52. 10 digits, that's 62. And let's say another 20 special characters. So there's only 72 different characters, for example. So let's say we have 10, so if the person's password is one character, we can try 72 possibilities. And if we miss on that, then we can try 2 characters, but then we have 72 times 72, which is 72 squared. And if we don't get any of those, we can try to get 72 times 72 times 72, all the way up to 72 to the 10th power. Very easy. Well, it's not easy because there's so many possibilities. So therefore, that's one of the reasons. That's one of the ways that we get security is the fact that trying to guess a password is very difficult. That's why we have passwords that are. How many bits are today's passwords typically for security? 128, 256, right? Typically 256 for a high security, 256 bits. Each of those bits could be what? 0 or 1. So therefore, the number of possibilities is 2 to the 256 power. That's a very large number, considering that 2 to the 20th power is a meg, and 256, you have about 10 of those. So it's a meg raised to the 10th power. So the idea is how to do it is very easy, but the time required to do it is very hard. So typically brute force algorithms don't work very well for hard problems. And that's how we can explain that. So the same thing can be said about our searching, pattern search. So let's say the text is going to be just a very simple string. We can think about each of the characters as being a text index 0, 1, 2, 3. So each of the letters can correspond to a particular index within the text. Now the text can be like this, or this one is only 12 characters, but it could have 12 million characters too. And it'll be a large file, would have many characters. And the pattern is going to be P. And again, if it's 4 characters, it's going to index 0 through 3. Okay, so we have n is the length of our text, 12 in this case, and m is the length of the string that we're searching for, which in our case is 4. And so the algorithm, brute force algorithm, we're going to try to match P0 to T0. And if it's a match, we're going to go to the next one. So if it's a match, just like in our longest common sequence, we're going to go to P1 against T1. If that's a match, then we're going to go P2 against T2. But if it's not a match, what are we going to do? Well, in the brute force algorithm, we would simply slide our pattern from 0 to 0, and we would match it up with 0 to 1. So if this is our pattern here, and this is our text, we try to match the pattern to the text as long as we can. And when we have a mismatch, we take the pattern, we slide it by 1, and we do it again. And we do it again. And eventually, if we're lucky, we're going to match, our pattern is going to match every single character. We're going to say it's a match. In the worst case, we're going to go to the end, and we're going to say we never were able to match it. So that's the idea of a brute force algorithm. What do you think about efficiency of brute force algorithms? It's not very good. It's not very good. All right, so so therefore, what would be the complexity of this brute force algorithm? We can say we compare m characters in the pattern about n minus n plus 1 times. That means starting the pattern at the beginning of the text and ending it n minus n plus 1 characters before the end of it, and each of those could be a full comparison. So therefore, we would multiply m by n minus n plus 1, gives us this number here. I guess this should be m squared. So usually m is much smaller than n, because we're searching for something small in a large text typically. So we say the complexity would be something on the order of mn. Again, this is small, this is a small value squared, this would be a square, and this is mn, that would be our biggest value. We typically think that n is much bigger than n, so that's going to be mn. So it will be, that will be the complexity. All right, so as an example, if we try to do a pattern match here, so our pattern is AC, and our text is this right here. So what we're going to do is we're going to match A to A, C to C, A to A. So far we have 3 for 3. But on the fourth character, we have a mismatch. C is not a match to B. So the brute force algorithm would say, okay, take the A in the pattern and now slide it by 1 character and go up, start matching it here. However, the brute force algorithm is doing something that's not necessary, because it's a waste of time. We can determine that that comparison is a waste of time. Comparing, trying to match AC starting here is not necessary. And it's a waste of time because P0, pattern 0, is not equal to pattern 1. What does that mean? It means that A is not equal to C. And since we already know on a mismatch here, we match the A and we match the C with the text. So the probability of matching the first character of the pattern, the text, is 0. So therefore the sliding of 1 is absolutely a waste of time. Does that make sense? Do you see why? Okay. All right. So we could then slide A, rather than going from here to C, let's slide it not 1 but 2 characters, so we can start with A and A. So we would match here, but that's also a waste of time. That's also a waste of time. Why is it a waste of time? Well, first of all, we know we're going to match A to A. How do we know that? Because we know that this character in the pattern, the third character in the pattern, is the same as the first character in the pattern. So if the third character matches the third character, then the first character on the slide will definitely match the third character. Okay? But we also know that the second character in the pattern is a C. And so is the fourth. And the fourth had a mismatch. So the probability of the second character matching the fourth is 0. So we can see that sliding once and sliding twice is a complete waste of time. We can do it, but the brute force algorithm is simply going to go through something which is definitely going to end up in failure. Questions so far? All right. Now, we're going to look at an algorithm, and I'm going to jump through the algorithm relatively quickly, but I'll show you the principles of it. It's called the KMP algorithm. Knuth Morris Pratt is an algorithm developed by one of the most famous algorithm designers, Donald Knuth. He is a genius. He was a genius. I think he's dead. And he developed a lot of great algorithms. One of them he did with Morris and Pratt. It's called the KMP, or Knuth Morris Pratt algorithm. And this algorithm is based on computing something called the next table. And the next table gives me information of what do you do on a mismatch. where you can eliminate all the possibilities that are going to fail based upon what we just saw, based upon our anticipation. If you look at our example previously, what was the reason that we could skip this double slide? On a mismatch here, why wouldn't we want to slide twice? What was the reason for that?
Because we knew our string already.
Because we knew that we mismatched the fourth character against the fourth, our C against a non-C. Therefore, sliding it twice would set up our second character, which is also a C, to try to match against a C. But in order for us to know that, we have to have a knowledge of our own string. So we have to know about our own string. So we have to sort of match our own string to our own string, if you will, to learn about our own string. And so what we're going to do is we're going to compute this next table. And so, for example, for the string ACAC, regardless of what text we compare it against, the first thing we're going to do is compare ACAC against itself, which is the principal part of the KMP algorithm, is computing the next table. The next table for ACAC is always -1, 0, -1, 0. Okay, that's interesting. So let's just assume that we know what that means. Let's just assume that we know what that means. Well, if we go back here, so that means we mismatched here, right? And so therefore, according to the table, we mismatched, we matched, matched, and then we mismatched here. The next table says 0. Do you know where we should compare next? We know a single slide is unacceptable, and a double slide is unacceptable. What do you think we should do? Well, you're saying triple slide, but I may not have ruled it out, even though we could rule it out. But can we rule it out? Can we rule out sliding 3 times on a mismatch here, sliding the A all the way up to the B?
Yes.
Or sliding.
Is it worth our while to slide 3 times?
No.
The answer is yes.
Oh.
The answer is yes. Okay, let's see why. Because when we compare A against on a single, double, triple slide, A is going against B. Now you might say no, and I know why you said no, because hey, it's not going to match a B, right? Not going to match a B. Well, I didn't know it's not a B. All I know it's not a C, because the next table doesn't know what you're comparing to. We don't keep track of the text. We only keep track of how we did against the text. So therefore, because we slide 3 times, all we know at this point is that the character that mismatched is not a C. Therefore, it might be an A. And so that's why KMP is going to say when you mismatch on the second C, compare the pattern at index 0. Index 0 for the pattern. What about the text? I don't see any information here. That's right. There's no information here. The information is implicit. And it means that if the number is a 0, which is 0, or a positive number, meaning not negative, if it's positive or 0, then it means the text index on the mismatch stays. We can always imagine that if we're comparing the text here against the pattern against a long text, at any point in time, the character in the pattern is indexed at I, and the text is indexed at J. So we're always comparing pattern I against text J. In the event of a mismatch, the next table is showing us the next value of the index for the pattern. So if we mismatch on the pattern at 3, the next pattern index is 0. If the next table value is non-negative, then the J index of the text doesn't move. So I moves from 3 to 0, and J stays at the location of the mismatch. That's what it means. Now, you might say, well, what the heck is a -1? Strange. What is a -1? So now let's take a look at what I want to show you is I want to show you a couple other patterns. So these are patterns of strings that generate the following next tables. We already saw ACAC generates -1, what is it? -1, 0, -1, 0. What do you think ABAB would generate? -1, 0, -1. How about XQ? Why? Because the pattern is the same. The first two characters are the same. The second and the fourth are different, but same to each other. Anything like that, the next table has to generate the same way. Okay, now let's take a look at the pattern here. ABC, ABD.
If we have AB, and third one is the same one.
We are not going beyond ACAC at this point, but now we're going to look at a bigger pattern. Now in this pattern, you're going to see that the next table has -1, 0, 0, -1, 0, and 2. So they're different values. And again, remember what I said. If the value in the next table is non-negative, then the index of the pattern goes to that non-negative value. And the index of the text stays at its current value where it mismatched. So that means if I am comparing, so this is index 0, 1, 2, 3, 4, 5. 5 means I mismatched on the 6th character of the string. It tells me the next comparison should be which character?
B?
No.
Or C?
The next character should be the C against which character in the text? Against whatever character
It is
mismatched
at J
mismatched the D.
with D.
So the question is, that is very exciting because I missed, so think about it. I'm starting here someplace in the pattern and I'm going in the text someplace and I match, miss. So I went 5 matches and a miss, or match, miss. That's what I did. I did 5 matches and a miss. And so the KMP algorithm says, okay, take not the first pattern, not the second, but the third, and slide it all the way over here to where you mismatched that last 6th character. So from 0, I go to 2, matching up to 6. Why? Anybody have an idea? Tell me why this 2 is there. Can you imagine what this looks like? Here's what it looks like. A matches A, B to, remember this is there's a text. The text looks the same. Match, mismatch. So what's in this character in the text? Not a D. It's saying take the A and slide it, take the C and slide it all the way to here. So it's as if you're comparing the 3rd character to the 6th character immediately. Notice what's preceding these two. What's preceding what's preceding the mismatched D?
2 matches.
AB, but notice that if we compare C against where D mismatched, then preceding the C is AB, and preceding the mismatch is also AB. So we are skipping comparing A to B in the text with the first 2 characters because we know that A to B already matched them in our own string further down, therefore the beginning is also going to match them. So we don't do things that are going to give us no success, and we don't do anything that we know is going to give us success. We just take the success and move on from there. We only do things that are uncertain.
Wait, we only do things that are uncertain?
We only compare when we are uncertain.
Oh.
So if we're certain that it's a mismatch, we don't do it. If it's certain that it's a match, we don't do it. We go to the next uncertainty. That's what KMP does. Okay? All right, now I want you to explain to me what -1 is. Now that we kind of understand what is non-negative. Let's look at this negative value. Let's say I match. So let's say I match here. No, let's say I mismatch right away. I mismatch. So the first character of the pattern is A. Text is not A. What would you want to do? If you were smart, what would you do?
Go to the next
String
character.
over.
So you mismatch the A, but you know nothing else. What's in the text? So you only know that A didn't match the text.
No, to the gift guide.
So you would go to the next character in the text with
With an A.
the same character from the pattern. So you would try to match this A against the second character in the text because it might match. Now, let's say you match here, but you mismatch here. A matches, the second A doesn't match. What do you want to do? Where are you going to go in the text?
Again, right?
Hmm?
Again, one iteration.
Okay, let me give you some numbers here. We're going P0, T0, P0, T0, P1, T1, mismatch. Now what am I comparing? What's my I and J value? Mismatch occurred on I and J at 1. What's the next IJ value? P,
P0 and T2.
P0 and T2 is exactly right. How about if we match, match, mismatch? P0 and T3. So, what did you notice always happens with -1 that never happened before? First of all, what happened with -1 with a pattern? Start easy. Starts at the first character. Very similar to what we got with 0. Remember that? However, -1, even though -1 and 0 are the same for the pattern, they're different for the text. In the case of a -1, what do we do with the text index? We increment the current J to the next one. And what do we do in case of a 0? We keep the text at J. How about at 1 or 2? We keep the J at the text, fixed. So the only time we move to the next J
If it's negative.
is if it's -1. Otherwise, we keep it. Okay. Can somebody tell me why we have a 2 over here? Explain to me why we have a 2 for the KMP algorithm. So the answer is going to be match, 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 mismatch right here. So it says compare this character in the text, which didn't match the D, with which character? With which character? The C. So slide this tick, 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 all the way here. Why C? Because what precedes the C is the A and the B. And so the C matches, A, B already matches. We don't have to check it if we know it's already going to match because we know our own string. We match the A, we match the B, C, here's another A and a B, and a mismatch. So A, B, C, A, B, D, when we mismatch on this, we already know that when we slide it, the A will match here, the B will slide here, so we just need to match the C to here. If it's not a match, then it's going to be a mismatch. Why is this a 4?
4 matching.
If I mismatch here, I'm going to move into 0, 1, 2, 3, 4. I'm going to try to match a B here because I'm assuming that 0, 1, 2, 3 are A, B, C, A, B, C, A, and here's the mismatch. Get the idea? See how that's working? So in the case of a 4, so let's assume that the index of D is I and the index of the text is J. I have a mismatch. What's the next index of the text?
The same position, the J.
J.
Yeah.
So it's J. And what about the pattern?
4.
4. Okay, so now you know how to use the tables. Okay, the calculation of the next algorithm is not simple, and I'm not going to go through it, but I want you to actually look at that and see how this table is computed, because otherwise we'll take all day. Yes?
So just to clarify, the
Yes.
2 and the 4 were, like, let's say the offsets in the array from 0 to that number?
Yeah, so
the
basically,
position from the beginning?
So let me answer your question with the following generic answer. Okay, not too generic. If the next table on a mismatch indicates a value of a non-negative value, or let's just say a positive value, that means the current element that you mismatched on should be compared with that positive value. And that means that that positive value minus 1 are already characters that will match the text from our knowledge about our own string. So if we have, for example, a 4 here, it means that the fourth character, which is the B, 0, 1, 2, 3, 4, the fourth character, which is a B, has the same, so the first 4 characters before it are the same as the 4 characters here. And that's knowledge of our own string. Notice that the next table is computed without knowledge of the text. It's irrelevant. So what we're doing in this computation, we're basically computing our own self-similarity. Okay, like I said, I'm not going to go through it, but if you go through it, you'll see exactly how these tables are assigned. So finally...
In the next table, is there any chance of getting negative values other than 1?
No.
Only minus 1?
Negative value, the minus 1 is really a special value. Minus 1 is equivalent to 0, except that minus 1 indicates that not only are you going to 0 in the pattern, but you're moving j plus 1 in the text.
Minus 1 indicates that whatever the position that we are moving.
Minus 1 indicates that we're definitely going to position 0 again on the pattern, but we're going to move it to the next location or whatever it was text, we're going to move to j plus 1 on the text. So for example, let's say pattern 5 mismatches text 100. 5 and 100 mismatch. The next table says minus 1. We're going to go to index 0 on the pattern into text index 101. If we mismatch 5 and 100, and the next table says 0, then we're going to compare pattern index against text 100. Any non-negative says J in the text stays the same. Any non-negative says J in the text stays the same. And the pattern takes whatever the next table says. Minus 1 is a special case where minus 1 means 0 for the pattern, 1 more for the text. That's it. And so the next algorithm here is, so this is basically how we're going to compute whether a pattern is in the text or not. So this is how we search the pattern. So assuming that M and N are moving through the pattern and the text respectively, this is a computation of the KMP algorithm. So you can see it's just an application of the next table. Okay, so I'm gonna kind of move ahead a little bit because I do want to cover a little bit more ground today. All right, so you can take a look at this, kind of work a simple example. I think if you work a simple example, it'll make a lot more sense to you. Okay, the next thing I want to do is I want to look at something which are permutations or orderings of strings. Okay, so a permutation of a string is basically the number of different sequences that you can make, or the number of sequences that you can make reordering all the elements in all the possible ways. If you look at the string cat, cat, you can see you can do cat, but then if you keep C fixed, you can permute T and A, or A and T, get T and A. And that's it. CAT, CTA, that's it. So now what you're going to do is you're going to switch A with C. Go original, switch A with C, and you have ACT. And you're going to permute every CT, so you get ACT, ATC. That exhausts all the possibilities. Now you're going to go back to the original, you're going to exchange T with C. So you're going to get TCA. And then you're going to permute all the CAs. So CA, AC, you got 6 of them. Those are all the possible permutations of cat. 6 of them. And if you think about it, 3 different letters, so it's 3 factorial. You have 3 letters to choose from, 2 letters, and then one is the last one fixed. But if you have, for example, a word like TCAT, TCAT, which is not a word, but it could be. Right? If you have 2 cats, one is SCAT, one is TCAT, you know. So TCAT basically could be a different sequence of characters. If you look at all the permutations, again, if there are 4 of them, then we can permute them in 24 different ways. However, when we do permute them, we find that some of them, marked with the asterisk, are the same. So are duplicates. So first occurrence of a permutation is an asterisk, but if it doesn't have an asterisk, that means what? That means it's a repetition. So the question is, how many unique permutations do we have?
By 2 factorial. By 2 factorial. I mean, there are 2 T's, so we divide by 2 by 2.
So, correct. So now let's look at the algorithm that can give us permutation generation. So this is a little Java program. This is a recursive idea, okay? And so essentially somebody sends me a string. In this case, I'm using a string buffer. Really, I should have used a string and then passed a string buffer here, but that's okay. Okay, nobody's hurt by this omission. So they gave me a string buffer, and then what I'm going to do is I'm going to call the recursive function, sending in, passing the string through, and then starting with an index int of 0. And this thing is going to basically, this index of 0 is going to be going through forward until it reaches the length of the string. Whenever it reaches the length of the string, I will output a permutation. So if the word is cat, C-A-T, then it's going to be cat is going to come in here, and then cat 0 will come in here. K is 0 equal to length of string? No. But notice that through all of the recursive calls, permute all, what am I doing with this value? Always goes up by 1. So the idea of this recursive algorithm is like this. So the string comes in. If it's not, now remember, the only way K is going to be equal to the length of the string when K actually goes off the string. Because the string of length 3 has indexes 0, 1, 2. So if it goes to 3, that means I'm finished with the string. That means whatever is there is that permutation. So what I'm going to do is I'm going to loop. So suppose I have cat, C-A-T. So I is equal to K, and K is 0. I is less than s dot length. So I will do how many iterations here in the loop? I will do 3 iterations. 0, 1, and 2. 0, 1, and 2. And then what I'm going to do is I'm going to exchange in the string K and I. 0 to 0, 0 to 1, 0 to 2. 0 to 0, 0 to 1, 0 to 2. Just like I gave you an example. Cat, C, and then permute AT. ATTA. Switch A with C. Permute ACT. CT, TC. So we're going to exchange, permute, recursively, exchange back. So this will generate all of the permutations, but it will not generate all of the repeated permutations, I should say. So if we want to compute the unique permutations, there's a few ways of doing it. One of the ways of doing it is I'm writing this formula here, which is a binomial coefficient. where this is the length of the string. This is a binomial coefficient, the length of the string minus j is going to index from the first to one previous character before me. So L1 is the first unique letter, L2 is the second unique letter, and LU of S is the last unique letter. We assume that there may be many letters that are repetitive. So, and US is the number of unique characters in a string. So if you have a string like tcat, US is going to be equal to 3, because it's only CAT are unique. If you have Connecticut, the two N's, two C's will be single unique characters. How many T's in Connecticut?
Two.
Two again. Okay.
3 C's.
3 T's?
3 C's.
3.
No,
C.
Connecticut.
2 or 3?
3.
Is 3? Did you write it out?
Yeah.
All right. Now, so what we're going to do is we're going to multiply. What's pi? Pi is a product. We're going to multiply for each unique letter in the string. We're going to do a product of these binomial coefficients. So for tcat, we're going to go from 1 to 3. For Connecticut, we're going to go from 1 to, I don't know, maybe 5. Whatever is the number of unique letters. We have to figure that one out. Okay, and so if the string is a sequence of A, B, C's, and D's, I'm going to first make an assumption that I'm going to permute that string so that all the letters that are the same are in order. The number of permutations of S is equivalent to the number of permutations of any other permutations of S. So the permutation S prime will be the same characters, but in sorted order. So you can see I have 3 A's, 2 B's, 4 C's, and 2 D's. And so therefore, my product of binomials is going to be 11, which is the length of the string, minus 0, 0, because I'm considering now how many of the first letter I have, and that's going to be L1 is A. So how many letters come before A? 0. So that's why I take 11 minus 0. Because I have 11 positions. Tick, 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 tick. And how can I choose 3 positions? I can choose 3 positions by 11, choose 3. Now, once I have that, I have how many positions left? Now I'm going to have 11 minus 3 by the time I get to the B's. So it's going to be 11 minus 3. It's going to be 8, choose 2. By the time I get to the C's, I'm already going to have 5 positions taken out. So it's going to be 11 minus 5. It's going to be 6, choose 4, because there are 4 C's. By the time I get to the D's, which are the last characters, I only have 2 spaces left and 2 D's, so it's going to be 2, choose 2, which is going to be 1. And when I multiply it together, I get 69,300. 69,300. That's a lot less. That's a lot less than 11 factorial, which would be about 37 million. That's a lot less than 11 factorial, which would be over 37 million. So 37 million, now we're down to 69,000. So these are unique permutations. And then I'm going to give you an algorithm. I'm going to modify my original algorithm to see how we can create the unique permutations only. Notice that it's still very similar. We still get a string, we say with 0, and then instead of permute all, we say permute unique. Same thing here, we output the string when k goes to the end of the string. And then here, we're going to create a set of characters called letters, L-E-T. And then what we're going to do is we're going to say, we're going to go through the whole string. We're going to say if k is equal to I, if they are the same, remember we're looping for I, but if k and I are the same, if it's our first iteration, or the character at I is not equal to the character at k, and the letter set does not contain the character at I, in that case, we're going to go into this exchange. What we're going to do is we're going to add it to the letters, we're going to exchange, we're going to permute unique, and then we're going to exchange it back. So this is going to skip all of the common ones by simply not exchanging letters that are the same, because they're not going to give us any differences, and keeping track of which letters we've exchanged in the LET set. Okay, so little analysis. Nothing wrong with a little bit of analysis. So we're going to count what is the unique permutation algorithm worst case. What's the worst case of the unique permutations? The worst case is when all the letters are different. So for example, if our permutations has all the letters A through Z, 26 letters, how many permutations do we have?
26 factors.
26 factorial, and that's a large number. How big? I don't know. It's very big. It's more than 37 million, I'll tell you that right now. It's way more than that. Okay, so what we have here is we're going to say, so essentially we're going to get, we can do this recurrence. So this is the permutation T of 0 is 1, and T of n is going to be n times T of n minus 1 plus n. So we can compute this, and this is our expansion by repeated substitution. And when we finish it, we end up with having this expression. If we repeat it I times, it gives us this expression. And finally, we end up with some crazy expression here. So you can see what it's going to be. Now that's the worst case, which is a very easy analysis in a sense, because it comes out factorial. If we look at the unique permutations, you're going to have n factorial plus the sum, as j goes from 1 to n, of n factorial over n minus j factorial. Okay, and if you recognize this sum is going to be very similar to what? This is going to approach e, because it's a summation of 1 over n minus 1 factorial plus 1 over n minus 2 factorial, etc., increasing all the way to 0 factorial. My last analysis, I'm just going to go through this quickly, so don't worry about the details of it. What we're going to do is we're going to use unique permutation analysis for the average case. And it's very difficult to define what average case is, but I'm going to toss in a parameter, p, for probability. So I'm going to say the probability is fixed. So probability is the probability that we have that same letter occurring again. Okay, so I'm going to put in a p here. And so if I simplify this repeated substitution, you're going to see this is going to expand quite nicely. If we repeat this substitution I times, you'll see that there's an exponentiating p, and there's also a budding factorial here, because it's basically n, n minus 1, n minus 2. This is getting bigger and bigger and bigger. Factorial. So as we continue, if we let from our general I substitutions I equal to n, we'll end up with p to the n times n factorial, where p is the probability. Think about what that means. P to the n times n factorial. That means that p is being raised to the nth power, but if p is large, what's the biggest number of p, what's the biggest value of p it could be? 1 is the biggest value, so therefore in the case of the p is the highest possible, this becomes n factorial. In the case that p is smaller, for example, if p is 1/2, then it's going to be 1/2 to the nth power. If n is 100, it's going to be 1/2 to the 100th power, which is going to be very, very small, but then 100 factorial will be very, very big. So this is trying, so as p is decreasing, this is trying to bring it down, okay? But n, as increasing, is always trying to bring it up. The question is, which function is growing more quickly, p to the n or n factorial? What do you think? Well, that's a good guess, but it's wrong. N factorial is growing more quickly. So therefore, as n goes to infinity, this function goes to infinity. Even with very tiny p, it will go to infinity. Now, but that's for infinity. We don't live in infinity, but it's interesting to consider it. But it's interesting to see what happens in realistic cases. So I have an example later on. So basically what we have here is this is going to be this part of it, and then this part is going to be dependent. Okay, so when we finish this part out, we can take the n factorial out. We have this situation here, and this basically becomes nothing more than a sum. Now, if p is equal to 1, then this sum is basically e. If p is 1, then this is going to be 1 over n minus 1, n minus 2, n minus 3, right, all the way down to 0. That's going to be e. So this is going to go to e as p is approaching 1. As p is approaching 0, this will go to 0. So if p is very, very close to 0, this will approach 0, therefore this term will disappear. So the bottom line is, notice that we have n factorial times p to the n, and we have n factorial times this thing, which is going to go no less than 0 and no higher than e. So this bracket goes between 0 and e. So therefore, we're going to call this bracket C, assuming that C goes between 0 and e. So therefore, it's going to be n factorial times Pn plus C. The worst case occurs when P is equal to 1. We already talked about that, right? When P is equal to 1, what's the value going to be here? That's going to be n factorial. But when P is smaller, P to the n is going to reduce the n factorial substantially. Right? So when P is getting smaller and smaller and smaller, this P to the n is getting smaller and smaller and smaller. What about C? It's also getting smaller. So as P is reducing, this whole coefficient is getting down. Okay, so now what I did here is I just basically did a little computation of what we might expect in this analysis. And again, I'm not sure how valid this analysis is, because we're saying P is the probability of the same letter being selected, which means that every letter has the same probability. Which is possible. It's not a terrible assumption, but it's an assumption. So what I have here is basically, I'm going to assume that n is equal to 10, so there are 10 characters in a string. I'm looking at the probability P is 0.1, 0.2, all the way to 1.0, so you see P's are increasing here. And because I have 10 terms, this is the computation of the constant C. Okay? This is the computation. So it's actually some interesting results come out. So this basically down here is P to the n plus C times n factorial, where these values, these 10, are the summation of all the bracket terms, the C, where there are 10 of them and then I sum them, 10 of them and I sum them. So this is the C component. Then I'm going to take P to the power of 10 plus C times 10 factorial. When I do that, so these are the values that I get. With the probability being 10%, I only get 4 unique permutations expected. Only 1/10 a chance. As this is increasing, as the probability is increasing, notice that what's going on here. I guess the probability has to be the probability that it is unique. So that all are unique. So basically, when the probability goes to 1.0, that's certain that all the characters are unique. In that case, this is the number of unique permutations that I have. Okay? So anyway, a couple string algorithms for you to think about. All right, let's continue. Okay, so let's look at some interesting notes from our text. So we want to do some deeper analysis on sorting using something known as a decision tree. So far, we decided that the best algorithm we have for sorting is what, in terms of complexity? Merge sort, and what do we say the theta was? N log n. N log n, okay. So in this case, what we're going to do is we're going to make the following comparison. Let's say we're going to compare, let's go start it here. So this is, all the sorting algorithms so far that we looked at are comparison sorts. For example, we did insertion sort, we did bubble sort, we did quick sort, we did merge sort. They're always comparing keys against each other. We only use comparison sorts to determine the relative order of the elements. Okay, so these are the ones we looked at. One of them we're going to look at is heap sort. We haven't looked at that one, but I'm going to come back to that. The best, worst case running time we've had is n log n. Is n log n the best we can do? And so we're going to employ a technique called decision trees that can help us answer the question. So let's say we want to sort, in this case, 3 elements. So the sorting sequence will be A1, A2, A3. We don't know what order they're going to be in, so therefore they could be in how many different orders?
3 factorial.
Assuming that they're all different, there's up to 6 different orders. So what we're going to do is we are going to go to the left on the decision tree if the ith element is less than the jth element. So if 1 is less than 2, we're going to go, if 1 is less than 2, we're going to go in this direction. So we know that 1 is less than 2. You get the idea? Now, when we decide is 2 less than 3, if that's true, then we're going to decide the sequence is 1, 2, 3. Why? Because 1 is less than 2, and 2 is less than 3, so the sequence must be 1, 2, 3. If 1 is less than 2, but 2 is not less than 3, then what we have is 1 is less than 2, and then we have 3 is less than 2. So now we have to decide, what about 1 and 3? Because we know now 2 is going to be the maximum value. So if 1 is less than 3, we're going to go 1, 3, 2. Otherwise, we're going to go 3, 2, 1. 3, 1, 2, rather. Does that make sense? Oh, no. I'm not hearing anything. Let's go try another one. So here, again, so these are relating to indexes. So 1 means A1, 2 means A2. Does that help? Okay, so 1, 2, so for example, if we compare A1, A2, if we go in this direction, that means that A1 is bigger than A2. That means 9 is bigger than 4. 9 is bigger than 4, that means that 4 is going to be bigger and 4 is going to be the smaller. So now we're going to compare what?
A1 and A3.
9 and 6. Okay, so if we decide that this direction, that means that 6 is bigger. So the sequence is going to be 3, 2, 1. Otherwise, the sequence is going to be 2, 3, 1. So basically, what we're seeing from the decision tree, that every time we do a comparison of 2 elements, we can end up in any of 6 different places. And the reason for that is because there are 6 permutations that can occur with 6 unique elements, and certainly n factorial permutations with n unique elements. Right? And if we have a few replicates, we're going to still attempt to go close to the same unique values. Okay, so you can see over here, the first comparison we're going to compare against element 1 against element 2, 9 against 4. Okay, and what do we decide? Here. We said 9 against 4 is here, so 9 is bigger. So now we're going to say, okay, what about 9 against 6? So we already know 9 is bigger than 4, what about 9 against 6? Okay, so 9 is bigger, so we're going to go in this direction, right? And then we're going to compare 4 against 6 to know how to place them. So we're going to go 2, 3, 1. And if this test was wrong, we go 3, 2, 1. So 2, 3, 1 means 2, 3, 1, 4, 6, 9. Okay, so that's our. So basically, the ordering is going to be looking like this. Decision tree can model the execution of any comparison sort, 1 tree for each input size. Algorithm is splitting whenever it compares 2 elements. The tree contains the comparisons along all possible instruction traces. The running time of the algorithm is the length of the path taken. The worst case running time is the height of the tree. Okay. So the theorem that we can make is that any decision tree that can sort n elements must have a height of n log n for a big omega, least possible. We know that the tree must contain at least n factorial leaves, because that's all the possible ways we can end up, since there are n possible permutations. A height h binary tree has 2 to the h or less leaves. It's 2 to the h if it's full, could be less than that if it's less full, right? So therefore, n factorial, the number of leaves, must be less than or equal to 2 to the h. Makes sense, right? So n factorial must be less than or equal to 2 to the h. 2 to the h is going to be what? What's 2 to the h again? Number of leaves. What's n factorial? Number of leaves. Okay, so therefore the height, h, we're going to take the log base 2 of both sides. If we take LG of both sides, then the h comes out, and then h is going to be greater than or equal to LG of n factorial. LG of n factorial. Now remember, LG of n factorial is going to be LG of n times n minus 1 times n minus 2 times n minus 3, which is LG of n plus LG of n minus 1 plus LG of n minus 2 plus LG of n minus 3 plus LG of n minus 4, because it's the LG of a product, so it's going to be the sum of the LGs of all the factors. Product rule for logarithms. Not going to get into that right now. You have to trust me on this one. There is a very famous formula called the Stirling's formula. It says basically that LG of n factorial is approximately LG of n over e to the n power, which of course can be rewritten as n times LG of n over e, which of course is n times the product of LGn minus LGe. When you distribute the n, you're going to have n LGn minus n LGe. And so what you have here is we have the proof that our sorting algorithm must be n LGn big omega. It must be no less than n LGn, no less than proportional or n LGn. Of course, this is just a constant, so it doesn't count. It's very small. So this is the growing term. Okay? So what does this show us? It shows us that comparison algorithms have to have a lower bound of n log n. So now we're going to look at another possibility of sorting. We're going to look at the possibility of sorting in linear time. Linear time means not n log n, but n, which seems to contradict our proof, which is always very dangerous, but always very exciting. What we're going to do is it's going to be a little bit interesting. Pay attention, it's not hard, but it's a little bit convoluted. We have an input of array of n elements. So we have n elements coming in. Each element is in the range from 1 to k. Each element is in the range from 1 to k. The output, the sorted output, will be in the array B, which is also 1 through n. So input is in A, output is here. And then we're going to have an auxiliary storage. We're going to have an array C. And array C will be counting all of the frequencies of the elements inside the original array.
What is K?
K is the maximum value in the array.
Like
So all the values in the array will be between 1 at the minimum and k at the maximum. You with me? Stay with me, pay attention. Here we go. Okay, so this is the algorithm. It's like, wow, forget about that. Okay, so let's look at this. This is much more fun to look at. So first thing we're going to do is we're going to do this. The first part is really easy. For I equal 1 to k, Ci is equal to 0. We like this part of the algorithm because we can see basically all we're going to do is put zeros into the C. Done. That's the first step, right? The next step we're going to do is we're going to look through here, and this is a little more involved. What we're going to do is we're going to put into C sub aj the value of C sub a plus 1. Remember, all the Ci's are 0. So what I'm going to do is I'm going to go through all the elements in the array from 1 to n, and I'm going to get the value of a sub j, which will be 1 through k. And I will take the value of that index in C, which is initially 0, add 1 to it, and put it in here. Every single time aj equals to a particular value, it will always go and add 1 to the same particular value. It will count the frequencies of the numbers. So let's take a look at that. So what we're going to do is we're going to put into C sub a sub 1. A sub 1 is 4, right? So C sub 4 gets the value of C sub 4 plus 1. It was 0, it goes to 1. Okay, see if we can anticipate what happens next. What's the next value of the j? J is going to go to 2, so we're going to assign C sub a sub 2. A sub 2 is 1, so C1 is going to get assigned. What will be assigned? It will be assigned.
C2 would be get assignment, Professor.
Say again?
C2 would be get assignment, Professor.
J is equal to 2. A sub 2 is 1. So C sub 1 is going to get assigned. So C sub 1 will be assigned whatever C sub 1 is plus 1. So you can see what's going on here is that we have the fact that we have 1, 4, and we have 1, 1. So the next value, J, is going to go to 3. When J goes to 3, then A sub 3 is equal to 3. So C sub 3 will be assigned. What will be the value? Whatever was C sub 3 plus 1. So this value will go to 1. On the next iteration, I goes to 4. And A sub 4, A sub 4 is equal to 4. So C sub 4 will be assigned. Okay? What will be assigned? Whatever C sub 4 plus 1, it means it's going to go to 2. And what that means is you can see that there are 2 4s in the array. And finally, you can see what's going to happen. We're going to assign into C sub 3 the value of 1 plus 1. It's also going to go to 2. Does everybody understand what this algorithm part did? So we basically put in the number of, now remember, 1 through k. Why 1 through k? Because basically these are the only values inside the array. We made that limitation. Okay, so now what we're going to do is we are going to try to place elements. This is when things get very, very exciting. So C prime will be the new value of C. Because right now we just have frequencies. But notice that the frequencies are in the sequence of values. We know there's a 1, a 2, a 3, and a 4. So what we're going to do is we're going to accumulate into the C prime array the number of elements there. So what we're going to do is Ci, as we go from 2 to k, Ci will get the value of Ci plus the previous. So we had this originally, so C2 will get the value of C2 plus the previous. That's how it gets to 1. This one will get the value of itself plus the previous, so it's going to go to
3.
And this one is going to get itself plus what's previous, it's going to go to
5.
Okay, so what this does, so the C prime array now has the sort of the distribution, or the distribution, a cumulative distribution of the elements. So now what we need to do is we're going to use this C prime to place the elements into B, which is, by the way, how many times did I compare the elements? 0. I never compared the elements.
Just placing the element.
I never compared the elements. I just indexed directly, right? So the next part is the last part of the algorithm. This is where things get a little crazy. So pay attention here. So where we're going to go is J is going to go from n down to 1. J is going to go from n down to 1. So, and we're going to be assigning elements AJ. So we're going to be assigning. So what we're going to do is we're going to assign A sub, which is, what's J?
And
What's J specifically? 5. So A sub 5 is assigned. Now, what is A sub 5?
3.
It's a 3. So I'm going to go into C3. C3 is 2. So I'm going to put this element into, so A, let's do it again here. So J is equal to 5. A sub 5 is equal to 3. C3. C3 is equal to, it was 3, right? So we're going to put into B3 the value of A5. Boom. This was 3, right? Before. Right? So we basically swapped C prime, this is C with C prime now. So this was 3, now it's 2. So why did we put the 3 here? Well, it told us basically from a cumulative standpoint that the 3 is at the 3rd position of the array because it's cumulative. So there are 1, 1 and 2s. By the time you get to the 3s, you have 3 of them. So therefore, put it at index 3. And then we're going to reduce this value from 3, we're going to reduce it down to 2. And now we're going to look at this element. So this element is A4. So A sub 4 has the value of 4. So C4 is equal to 5. So B5 gets the value of A. So B5 gets the value of A4. And so what's going to happen is this is going to go into here. And we reduce this down to 4. The next element is going to be 3. A3 is equal to 3. C3 is equal to 2. So it's going to go into position 2. And we decrease this one. So this one says that you have only one element from 1, 2, and 3. Because we've taken care of the other ones. That's what we have remaining, actually. So now we're down to which index?
1.
Index 2. Index 2. So A2 is going to get placed. A2 has the value of 1. C1 is 1. Which means it's the first element. That means there is a 1. So it's going to get put into index position 1. We're going to reduce this to 0. Okay? And so the final value is going to be when j goes to 1. A1 gets assigned to, what is the value of A sub 1? It's equal to 4. C sub 4 is equal to 4. It's going to go into B sub 4. Notice that the numbers are sorted. Notice that we never compared the numbers. Okay, so you saw the code, not the code, but you saw the algorithm. Now, this algorithm, if you look at it, so this is the first thing we do, put all the zeros in, right? Then we're going to do what? Then we're going to do all the frequencies, right? Then from 2 to k, we're going to move this and count the cumulative frequencies, right? So put the zeros in, put the frequencies, put the cumulative frequencies, and then move the stuff where it belongs. Notice that the complexity here is theta k, where k is the number of unique values in the array from 1 to k. This is theta n. This is again theta k, because you're doing this array. And then finally, we have theta n. And so the whole complexity of the algorithm is a bunch of n's and a bunch of k's. It's going to be theta n plus k. So if you have very few different numbers, k is going to be pretty small, and the complexity of the algorithm will be linear. So k is equal, now if k is equal to theta n, what does that mean if k is equal to theta n? Or big O of n. What does it mean, k element of big O of n? What does that really mean? No, but what does that really mean? What does it mean if k is big O of n? What's k?
The maximum number of your
Number of unique values, right? Okay. Then the counting sort takes theta n time. But we said sorting takes at least n log n time. So what's the problem? What's the fallacy? Basically, comparison sorting does take n log n. Counting sort is not a comparison sort. It's a different kind of sort. It's a sneaky sort, right? In fact, not a single comparison between the elements. Counting sort is what we call a stable sort. It preserves the input among equal elements. It means that if you have 2 4s and they're out of order, when you sort them, they're going to keep the same order as they had in the initial array. So it's a stable sort, means that it's not going to switch equal elements relative to each other. Okay? What other sorts have this property? So you can see what's going to happen here. The 3s originally were here, but then they moved into these locations. They're still left and right of each other. The 4s were left and right of each other, and notice they end up left and right of each other. So it's a stable sort. Okay. There's another sort called the radix sort. How many of you have heard of the radix sort? Nice. Huh? Oh. Okay, there you go. All right. right, so there you go. So say a radix sort, so we're going to look at a radix sort with base 10. Now, you know a radix sort takes into consideration the base, right? The base. And in this case, we're going to consider base 10. The base 10 has digits 0 through 9. So let's suppose our original data looks like this, and we want to sort this data. So what we're going to do is we're going to process this data in this direction, going upward, but we're only going to consider the least significant digit. So therefore, if you go up through here, you'll see that the highest significant digit is a 9, so 839 is going to go here. And as I go upwards, I see another 9, so 329 is going to go here. And as I go up again, I know that now I'm looking for the next biggest number, so I can see 657 and 457, right? And then the 6s, I have 436, and then I have 355, and finally I have 720. Now you might say, well, what the heck is the complexity of what I just did here? Anybody? Hmm? Of what?
No comparison.
I didn't do any comparisons of the elements themselves. I just looked at the digits, right? So here's how this is actually implemented. Check this out. So what we're going to have, this sequence of numbers. Now it could be a mini numbers. It just happens to have a few of them. Imagine that I create queues, FIFO queues. And the queues are going to be the 0 queue, the 1 queue, the 2 queue, 3, 4, 5, 6, 7, 8, 9 queue. There's going to be 10 queues altogether, from the 0 queue all the way up to the 9 queue. I look at the first number, and only I look at this digit, I immediately put into the 5 queue. Immediately. Okay? I look at the second number, it goes into the 0 queue. Are you with me? Okay? Then I'm going to go to the next number. It goes to the 6Q, 9Q, 7Q, 7Q, 9Q. What was the complexity of that? N. Now what I'm going to do is I'm going to take the 9Q, I'm going to append to it the 8Q, 7Q, 6Q, 5Q, 4Q, 3Q, 2Q, 1Q, 0Q. When I do that, I will immediately produce this. What's the complexity of that? Theta n. So what's the complexity of both those operations? Theta n. Okay, so that's cool. So basically I can do this using these queues by segregating them on queues and then merging them with queues. So once I do that, I'm going to go to the next pass. The next pass, I'm going to look at the second least significant digit. And again, I'm going to split them up into queues, then I'm going to link them. But for us, we're just going to kind of parse through them. We're going to see that the first number here, the biggest number is a 5. So 657 is going to go here, 457 is going to go here, and 355 is going to go here. So after all the 5s are taken care of, the next biggest number coming up is going to be a 3. So 839 goes here, 436, then we're going to get 329, and 720. Again, split them up, merge them up, theta n. So that's 2n amount of work. So now, what I want you to notice is I want you to notice what the data looks like right now. It's not sorted. The numbers are not sorted. But if you look at the sequences, look at the last 2 digits. What's the number here? 20, 29, 36, 39, 55, 57, 57. It looks like the 2 digits, the least significant digits, are sorted. So now what we're going to do, we're going to segregate them and spread them across 10 queues. So notice that we're going to get, the first thing we're going to find is an 8. It's going to go to the 8Q, right? So 6Q, 4Q, 3Q, 8Q, 4Q, 3Q, 7Q. And then 8Q is going to be first, followed by the 7Q, the 6Q, the 4Q, the 3Q. Now the numbers are sorted. We preserved the order. It's a stable sort. Notice that before, on the numbers that are the same, notice that the 2 4s, see the 4 here and the 4 here? 4, 5, 7 stays here. The 4 was lower than this one. It's still lower than this one, which is good because lower means bigger. So we sorted them. So what's the complexity of radix sort? Complexity of radix sort? Well, you could say it's theta n. but precisely you should consider the fact that each number has a certain number of digits. And so therefore, since each number has a certain number of digits, we need to split them into the queues and merge the queues the number of times that there are digits in each number. So if the number has 3 digits, we have to do it 3 times, and the number has 25 digits, it's 25 times, but we don't do any comparisons. So if k is quite small, not k, if the number of digits is quite small, then this algorithm approaches linear complexity. Because then a quite small number, basically, you could say if the number of digits is d, and the number of numbers is n, we could say that complexity is theta dn. But if d is quite small, you could say, well, d really, if it's only got 8 digits or 16 digits, you can say, well, it's just a constant. So the sort approaches linear complexity, or is close to linear for small d. Okay? The book gets into some other analysis here. So one of the things that they want to do is they want to prove here induction on the digit position. Assume that the numbers are sorted by their low order t minus 1 bits. So t minus 1 means that this is t minus 1, t minus 2. So they are sorted on the pink bits. So therefore, now we're going to sort on digit t. And we can see that as we sort on digit t, the first value is going to be 8, which is going to move this value here. The second value will be 7, it's going to move this here. So we can see that it will be a stable sort. So these numbers will go in the appropriate sequence, meaning 8 all the way down to 3, which is here. And the numbers that are the same will stay in their relative orders. So it will be a stable sort. And since these are already sorted, if we put a stable segregation on the most significant digit, we're going to have the number sorted. And that's the proof there. So you can see over here.
You can go either way too, right? You can start from the top and go down.
Depends what you're trying to do. Yeah, I mean, so right now we're going for ascending. If you want to go descending, you can certainly do that. You can certainly link them that way. Yes. Okay? So you can see that basically these two numbers here, right? So two numbers equal in digit t are put in the same order as the input, which implies the correct order. So that's the idea here. And then they go into a little bit of proof that I'm not really crazy about. I can actually show you a different way of analyzing it. But the bottom line is we know that we have to split merge d times, when d is number of digits. Now, you can think about it this way. Suppose that I have an array of 1,000,000 numbers. And they are, in fact, integers. To make it easier, I'm going to say they are non-negative integers, so 0 or higher. So integers can go quite big, especially if we're talking about 4-byte integers. They can go into very large numbers, 4 billion, blah, blah, blah. So let's say I have 1,000,000 of these numbers. So let's say I wanted to implement radix sort on those numbers. What do you think is the easiest way to sort them? In terms of, you understand that if I sort them by numbers internally are stored zeros and ones. So if I do what I did in the example here, which I had 10 digits, then I have to split them into 10 queues, and then I have to merge 10 queues back to each other. But if I only had 2 queues, it'd be kind of cool. And that could work, for example, if I took each number and I went to the low bit and I just looked at the 0 or 1 and put into a 0 queue or a 1 queue. I did it 1,000,000 times. I only have 2 queues. Then all I need to do is just put the queues back to each other. Then I would separate them again by the second bit. Okay, 2 queues, put them back in. Third bit, all the way down to the last 32nd bit. And the numbers would be sorted. So that's using the base of the radix sort, which radix means base. The base of the radix sort would be 2. And the base essentially is the number of queues that you split your data into. So the sort we had up on the board, that was base 10 radix. And if you use base 2, you have to mask out individual bits, but it gives you only 2 queues to use. So it's much simpler, much quicker.
Storage. Less storage. Less.
Less management of data structures. And then if you're using something like a Java program, for example, or if you're using C++, you can use STL and C++, or you can use Java, for example, what do you call those? Array...
Collection.
You can do it. Array... Java people? Nobody?
Collections, array list.
Array list.
Oh yeah, array list.
Array list. And just use an array list. So look at the bit, and just take an array list, and just add. The problem with those lists is that you never know how long one list is going to be. If you have 1 million numbers, any one of the lists at any point in time could take 1 million elements. Because maybe they all have the same bit in position 75, in position, let's say, 12. So if you have 10 lists, then you have problems because any of them can grow. But if you have 2 lists, it's a little bit easier. You need maybe less space if you're going to allocate it. If you're going to use dynamic programming like STL and C++, or array lists in Java or something like that in C#, then those lists are going to grow automatically, although you probably, for performance, even if you have an array list, you still want to say, if you have 1 million numbers, you anticipate 500,000 numbers going into each array list, roughly. So what you might want to do is you might want to correct for some randomness, and say, okay, I'm going to create an array list, and I'm always going to have the array list go to 600,000. In case it has to go to over 600,000, it's going to do its own thing. And it's going to get larger if it needs to get larger. You follow what I'm saying? Okay, so did a few things today, right? A little bit string searching. Please look at that KMP algorithm. See if you can figure out how that next table is created. It'll take, you need to go through an example of doing a couple of strings. Do a string like ACAC and then do one like ABC, ABD. You can do that, you'll get it. Okay. Yes. Oh, for submitting the homework, which was due today, so I'll have to set it up. I'll make it so it's due by tomorrow, so to upload it.
So you create.
Huh?
I created it.
You created it?
Yeah.
Okay, so by end of today, we should have it. Okay, so by end of today, upload it. Thank you.